Um, so people often think, your intuition for a lot of people tells you um, that in any collision, or in lots of collisions at least, there's sort of a winner of the collision and a loser of the collision. Um, so in a collision, there's a winner and a loser. Um, you can imagine, like, um, if a semi truck hits a um, something that uh, doesn't scream out in pain. Yeah, a person would. So that's the uh, hits a small wagon full of pumpkins. Whew. Um, then the truck is going to smash the pumpkins. Like, the truck is going to see things fly, but it won't really feel much of an acceleration. So you think like the truck wins that collision. Okay. And people tend to think that whatever the thing is that wins the collision applies a larger force to the other thing than that thing does. So how am I going to say this? There's a winner and a loser, and uh, the winner applies a larger force than the loser does. That'd be sad if I was talking about a person too, because then besides being hit by a truck, we'd be calling him a loser. Um, and that's okay. So that idea makes sense. Like, you think a truck hits something little, and the truck must be applying a much bigger force to the wagon or whatever than the wagon is to the truck. But the truth is, both of those two things, in anytime two objects are in contact, each thing applies the same magnitude of force to the other thing. It's a sort of a counterintuitive idea in a lot of ways. Um, but really, um, in any kind of contact between two objects, so that could be like a violent collision, or it could just be two things pressing against each other. Um, but in any contact between two objects, the magnitude of the force that each object applies to the other is the same. Okay, so think about that for a second. That, uh, in a lot of ways, I think that doesn't make much sense to a lot of people. Like, so imagine, like, a football team running through a tunnel at the stadium and smashing through a piece of paper. Like this giant, like 100 people who all weigh 250 pounds running as fast as they can, going through a piece of paper. And this is saying that at that instant of contact, before it rips, the paper is applying the same force to the ball team as vice versa. And that feels odd, but it really is the case. And it's not like a trick or anything. That just is how it is. Um, so the idea of the winner and the loser, like when the football team smashes through the sign, the piece of paper, the football team sort of wins that collision in some sense. Um, but that has to do with other things besides the amount of force that's applied. So say that you can apply 50 newtons of force to a piece of paper before it rips. I don't know how much you can, but so the front line of the football team runs into it. They keep running until that force gets up to 50 newtons. And at that point, the paper is applying 50 newtons to the football players, and the football players are applying 50 newtons to the paper. Then the paper rips, and the force goes away on both of them, and that's how it is. So the idea of like who wins the collision and who loses the collision has to do with other stuff unrelated to the amount of force. And I'll talk about that now. So which object wins or loses? Isn't determined by the contact force. Okay, so this is Newton's third law. And Newton's third law says, well, in the original text that Isaac Newton wrote, it says something like, for every action, there's an equal and opposite reaction. It's in Latin, so that's a rough translation. But that's the sentence that you maybe have heard before. For every action, there's an equal and opposite reaction. It's pretty hard to use that statement mathematically at all. So we're going to use sort of a different form that says the same thing. And so the way we're going to think about this, so we'll think of it as if two bodies A and B are in contact, then the force vector that's on body A applied by body B is equal to the negative force vector on body B by body A. Okay, so that's really that's a more useful mathematical statement of Newton's third law. Or another way to think of it is if you have two objects that are in contact. So let's call, so let's say, well, this is body A, and it's in contact with, there don't have to be any restrictions on the kind of object we're talking about. So let's say body B is that. Then the free body diagrams, the free body diagram of A would look something like this. There would be a downward weight force that's equal to, I don't know, that's the weight. And then there'd be a normal force. I don't care about these right now. The one that I care about is contact force that's applied to A by B. In this case, those two are pushing on each other. So this force is going to be toward the chosen body. So it'll be directed to the left, and I'll call it R. And then when we do the free body diagram of B, there's a weight force that I don't care about here. There's a normal force. There's a friction force. And then the contact force is going to be the same magnitude in the exact opposite direction. So these two have the same magnitude and they're in the opposite directions. Any questions about that? Yeah. Okay, so that's a good question. We were just talking about that. So if if you applied a force, say this was on rollers, okay, and you pulled on this, okay, the question is kind of what would happen between these two. I haven't really drawn enough detail for you to know what's going to happen. But let's say that if you pulled on this and got this moving that way, it would make A follow it. Okay. Then the way to think about that, well, we know they're not pushing on each other. Okay. But to know whether it's tension or not, imagine replacing that contact between them with a little cable between them. And ask yourself, would the same thing happen? Okay. So if you pulled on this and there was a little cable in between here, that cable would also make A follow it. A would do just the same thing it did before. And so that idea of replacing the contact with a cable means that it's a pulling force. So I think, to me, that's a sort of a useful way to think about those two things. And a pushing force, a pushing force on the other hand is like these two things are trying to mash each other. Like if you thought of them as being made out of tissue paper or something, would one of them collapse? Okay, or would both of them collapse? So if instead of applying the force this way, you apply the force to A this way, that's going to push B that way. If this was made out of tissue paper or origami, when you apply this force, that would squish, and so that's a pushing force. That's the idea I was thinking of here, yeah. Yes? What is the arrow on the free body diagram? This one? Yeah. That's a friction force because, yeah. But for this, the only thing, I just was too anal to draw a free body diagram without putting all the forces in, but all I really care about for this discussion is those two R forces. Okay, so let's think about, so there are some aspects of this that I think make sense to people intuitively and some things that sort of don't. And I want to kind of address both of those sort of things and maybe help you start to make sense out of this. So your intuition about this is sometimes right and sometimes wrong. Intuition is sometimes right about this. Okay, so think about this. So it's like a warm spring day and you're like at the park having a barbecue, you're barefoot, I don't know, maybe you shouldn't be barefoot at the park. Maybe it's at your house. But anyways, a soccer ball rolls over, okay? And and you look up and there are a couple kids who are playing soccer just, you know, 20 feet away from you or something, and they ask you to kick the ball back. Okay, you're barefoot. So picture that. Think about the size of a soccer ball. And you just nudge it back over there, no problem, right? So now think about the same thing happens, like you're barbecuing barefoot and a ball rolls over and you look up and these kids are like 50 yards away and they yell for you to send the soccer ball back over. So you like look down at your bare feet and the ball and you think about how hard you're going to have to kick the ball to make a ball travel 50 yards. And you know intuitively that it's going to sort of sting your foot to kick a ball that hard. Okay. And so the way that works is that if you're going to, so if you have to apply a big force to the ball to make it go, there's no other way around the fact that that ball is going to apply an equal and opposite force to your foot. And if you're barefoot, that force can hurt, you know? So in that sense, it sort of makes sense to you. You're used to this idea in some ways. Um, so for example, um, kicking a ball hard when you're barefoot. And then there's sometimes that it just doesn't really make much sense to you at all. And it's sometimes wrong. Um, so a case where I think this doesn't make a lot of sense to people is imagine like a pro baseball game. Um, so ball comes in at 100 miles an hour. A 200-pound guy hits it back the other way at 110 miles an hour or whatever, you know. Um, so there's a contact for a short amount of time between the bat and the ball. And that contact leads to the bat just basically doing like the bat and the batter look like it looks just the same as what it would look like if they missed the ball. But the ball exactly reverses course and flies 400 feet in the air. And so, like, the question is, how is it possible that the the ball hit the bat with the same force the bat hit the ball? I think that doesn't make a lot of sense to most people. Um, so the example here is a batter hits a baseball, 400 feet, say. So let's just try to make sense out of what's going on in this baseball example. Um, so first of all, uh, and so you think like, okay, well, if they applied the same force to each other, maybe like half the time the baseball would go flying and half the time the baseball would go right to the glove and the batter would go flying 400 feet or something, but that doesn't happen. I've never seen that. Um, so what happens though is when they're in contact, there's a huge force that the bat is applying to the ball, and there's an equal and opposite, the same magnitude of force, just acting in the other direction, force that the ball is applying to the bat. And then now think about it in terms of like a free body diagram. So a baseball weighs like 1/10 of a kilogram or something. If you apply, I don't know what the magnitude of that force is, but it's got to be huge. Let's say 5,000 newtons or something. If you apply 5,000 newtons to something that's in the air, that has a mass of 1/10 of a kilogram, that big force is going to make it accelerate a lot. Okay. I mean, think of Newton's second law, you have F equals ma. So that force of 5,000 is equal to 0.1 times the acceleration. So that baseball is going to have an acceleration of 50,000 meters per second squared. Okay. But now think about what that 5,000 Newton force is going to do to the baseball player. Okay. So, well, first you can think about the bat because it's really hitting the bat. The bat weighs more than the baseball, but that isn't really what the thing is. The thing is that the bat's being also held by a 200-pound person. And then that's not even really what it's about because the baseball is in the air. The batter isn't in the air. The batter has cleated shoes stuck into the ground. So it's a 200-plus-pound system of a person and a bat. And the person's feet are dug into the ground. And so it just comes out to, even though that force is the same, that contact force is the same, the bat has a huge number of advantages for keeping it from accelerating. Okay. And so it isn't really about the difference in the force. Those have to be the same. That's Newton's third law. It's just about what else is going on. Okay. Anybody have any questions about that right now? So let's see. My example, the batter hits a baseball 400 feet. It feels sort of like the bat applies more force to the ball. So it applies more force to the ball than vice versa. But really, that force magnitude is the same. It's just that, so it is just that that force accelerates a ball a lot more than it accelerates. Sorry, this is wordy. Then it accelerates a bat plus man combination standing on the ground. Okay, so what happens as a result of this collision isn't determined by a difference in the force. It's just determined by what else is going on. What are the masses of the two different things? What are the other things touching? That sort of stuff. And then, by the way, think of also any of you who played baseball or softball or whatever. I don't know. Do in softball do you ever break bats? I guess you use aluminum. Everyone uses aluminum bats now. Well, we used to use wooden bats, and sometimes we would get broken bats when I was like 10 or 11 years old. But our pitchers threw, let's say, 50 miles an hour maybe or something, and so if we got a broken bat, it just made sort of a funny noise, and the coach would bang it on the ground and hear a rattle and say, like, okay, the bat's broken. Have you ever been to a Major League Baseball game where they break a bat? It's a totally different thing. They hit the ball and the bat just like explodes into pieces, like pieces shoot out everywhere. And what that is the fact that because there is a lot more contact force in a Major League Baseball game when a player hits the ball than there is in a Pee Wee baseball game, the ball hits the bat with enough force to make the bat splinter. So in that sense, you know, you're sort of aware of this dynamic. Um, there are, in that intuition test that we took at the beginning of the year, the first lab of the year, uh, we'll, we'll do the post test at the end. It's like the bubble sheet test. Um, that test and other tests like it will often say like, okay, so they'll set up a scenario like, okay, there's a truck rolling in um, and it's going 10 miles an hour and there's somebody like jogging away from the truck to try to get away from it, but the truck catches up and they collide. Um, which force is bigger? A, the force the truck applies to the runner. B, the force the runner applies to the truck. And Newton's third law says in that case and in every case, the magnitude of those forces is the same in opposite direction. Oh, uh, I didn't fit this in the way uh, I wanted to, but I want to give this example. Oh, remember when I ran into my old physics teacher? I'm going to give an example from my high school physics teacher, but it's the other one, not that guy. Okay, so my physics teacher was like probably late 50s and very, very out of shape and like a sort of typical like physicsy nerdy kind of guy. And when I took the class, Mike Tyson was like this hot new up and coming, like he hadn't won the uh, heavyweight championship yet, but everybody was like buzzing about him because he like knocked everyone out really fast. And this guy, we're talking about Newton's third law, and he's like, you know what? I wish they would give me a chance to fight Mike Tyson. I guarantee you, if I got a chance to fight him, I could hit him exactly as hard as he hits me. And he drew this picture that was like, I wish I had the original picture. It was an arm like this. So that's Mike Tyson. That's Mike Tyson's arm. And then here's his face. And it's funny because um, you don't normally think of it this way, but it's literally true. Like if you drew these free body diagrams, um, like a free body diagram of the glove, it's a pushing contact, right? Um, they're not pulling, they're pushing. And um, so here's a free body diagram of the face. Okay, so on the face, there's a force here of, uh, let's say, 2,000 newtons. I don't know how much. And Newton's third law says that that means that the force here is 2,000 newtons. That's it's not like a trick interpretation of it. That's really what it says, and that's really how it works. Um, but the thing that makes it funny is that it's a very bad boxing strategy to try to beat up a guy's fist with your face. Um, the direction is shown by the arrow. Yep. So the way we're going to use this most of the time, we're just going to keep the same label on it, either the same variable or the same number, And we're just going to switch the direction of the arrow exactly backwards. Okay, let's do this in a problem or two. Okay, so let's say that we have 3 carts in a row. The first one on the left is 1 kilogram. And then the middle one is 2 kilograms. And then 3 kilograms. And let's say that on the left of the 1 kilogram cart, there's a 20 Newton force applied that direction. And then on the right of the 3 kilogram, there's a 10 Newton force this way. And we want to know what's the force vector applied to the 2 kilogram cart by the 1 kilogram cart. Okay, that's what we want to know. We're not asked explicitly for the acceleration, but you might remember that in a problem like this, if you don't know the acceleration of the carts, that's always the first step that you have to make. You have to isolate everything together as a single system and calculate the acceleration. So first, isolate all 3 of these together and calculate the acceleration. Why don't you take a minute and see if you can work through that and ask me questions if you get stuck and talk to each other. But isolate all 3 together and calculate that acceleration. So first, I'm going to draw a free body diagram of all 3. So there's a weight force straight down. That's equal to the total mass times 9.81. So 6 times 9.81 is 58.86. And then there's a pushing contact up from the ground. I'll just treat that all like it's acting at one place. So I'll call that N total. And keep going around the boundary, and you get to the 10 Newton force pushing to the left. And then on the left, you have the 30 Newton force pushing to the right. And that's everything. And then Newton's second law says 30, 0, so the positive x direction, plus 0, negative 58.86. Oh, yeah, sorry, I just wrote it down wrong. Okay, and then there's the weight. Then the normal force is 0 N total. And then the 10 Newton force is in the negative x direction. So a negative 10, 0. And all that's equal to the mass of our system, so 6, times the acceleration, and the acceleration is in the x direction. We're using the coordinate system that we always use for rolling and sliding problems. That's with the y-axis pointing right out of the surface. And that means the x-axis is this way. And in this problem, that's nice because it turns out to be the coordinate system we're used to. That's how we always want to treat rolling and sliding problems. And then the only equation that we care about in this case is the x equation. It says 20 plus 0 plus 0 minus 10 is equal to 6a. And so 10 is equal to 6a. And so a is equal to 1.6 repeating meters per second squared. And then the acceleration vector is what we get when we plug that value of a in for this vector. And so our acceleration vector for everything in our system is 1.6 repeating for x, 0 for y. Meters per second squared, or that's in the positive x direction, so you can also think of it as going this direction with a magnitude of 1.6 repeating. Okay, so now that we have the total acceleration, now we can isolate individual carts to figure out what the contact force is. We're trying to figure out the force vector applied to the 2 kilogram. So your first thought would probably be that you want to isolate the 2 kilogram part. But in this problem, where the one that we want is not at either end, that would cause a problem. I mean, you could still do it that way, but you couldn't do it in one step. So it's not the best way to do it. The problem is that if you isolate that 2 kilogram cart, you have an unknown contact force from over here going that way, and an unknown contact force from over here going that way. They're both x components, which means we have one x component equation for 2 variables, and you can't solve for that. So there are sort of 2 ways to do this, and both of them are sort of, like tricky in their own way, kind of. The first way, let's do this way first, is we're going to isolate the 2 and the 3 as a single unit. Okay. Then it's like we have a single object that is all the way at the right end of our train of objects. And then the only unknown force we have is the contact force applied by the 1 kilogram, which is what we're looking for. Okay. So take a minute and isolate the 2 and 3 kilogram carts together and calculate that contact force. So we're going to calculate the force vector on the 2 by the 1 this way. Okay, so this time we're going to isolate the 2 on the right side. So isolate the 2 and 3. The weight force is the total mass, 5 kilograms, times 9.81, so 49.05. And then there's a pushing force up, I'll call that N23. And then this force is the 10 Newton force, right? Pushing this way. Okay. And then that 20 Newton force on the left side is not applied here because it's not in contact with the boundary, you know. This doesn't feel that. The only other place where there's contact with the boundary is the contact force from the one. So there's a pushing force this way. That's the force vector applied by the one. And I'm going to call that R. And that's it. So Newton's second law says R0 plus 0, negative 49.05 plus 0, n23 plus this 10 is in the negative x direction, so plus negative 10, 0 is equal to the mass of this system, 5, times the acceleration vector of this system, which is what we calculated in part A. So that's 1.6 repeating for x, 0 for y. And what we're trying to calculate is this vector. This vector here is the force on the 2 by the 1. So the x component says r plus 0 plus 0 minus 10 is equal to 5 times 1.6 repeating. So that is 6, 8, thank you, 8.3 repeating. And now you can solve for r, and you get that r is equal to 18.3 repeating. And so that means if you plug that back into the force vector, we just didn't know what the value of r was, you get that the force on the 2 by the 1 is equal to 18.3 repeating, 0. Or another way you can think of that is that's in the positive x direction, so you can think of it as going this direction with a magnitude of 18.3 repeating newtons. Okay, so that's one way to do this problem. But I'm going to do it the other way now, using Newton's third law. And even though I always think these are sort of like it's sort of cool to see how this works, I think, because so we just isolated these two, and into that equation we didn't put anything about this 20 Newton force. Okay. Now we're going to isolate this one. We're not going to put in this 10 Newton force, but we're going to get the same answers. Either way, they have to match. And your first thought, I think, is how do they know what's, when I isolated these, how did they know this was here? When I isolate this one, how is it going to know this is here? And the answer is they know because we had already calculated the accelerations using both of those. So even though the forces weren't there, that information was brought over from part A. But the main thing I want to do here is I'm going to isolate this. We're going to calculate the force on 1 by 2. That's not what we're asking for. We want the force on 2 by 1. But if we can calculate the force on 1 by 2, then Newton's third law says all we have to do is switch the direction, and that's the answer. Okay, so for this one, I'm going to isolate the 1 kilogram cart. And I'm going to use Newton's third law. Okay, so free body diagram of the 1 kilogram. We have the downward force of gravity. That's 1 times 9.81. The upward normal force, I'll call that N1. We have the 20 Newton force pushing this way. And then the only other contact force is the one applied by the 2 kilogram cart. So that's going to be pushing like this. So I'm not using anything that we calculated in part B. We're doing everything totally over again. Like these are two different ways that you could approach this problem. Okay, so now Newton's second law says 20, 0 plus 0, negative 9.81 plus 0, N1 plus negative R, 0 is equal to the mass of 1 times the acceleration of positive 1.6 repeating 0. And this vector here, what's that force vector? We don't know R yet, but what's it going to be once we plug R into it? Well, I just meant like the name of it. So just identify what that force is. So this is the force on the 1 by the 2. But yes, it is right. And so all we want to do is figure out that R value. So the X equation says 20 plus 0 plus 0 plus negative R is equal to 1.6 repeating. And so R is equal to 20 minus 1.6 repeating, or 18.3 repeating. That means that, so if we plug this value for R into the vector, we get that the force on 1 by 2 is equal to negative 18.3 repeating 0. Or we can also write that as a magnitude of 18.3 repeating in the negative x direction, so this way. And so we're talking about a single contact force. If you're talking about the relationship between the force on 1 by 2 and the force on 2 by 1, that's a single contact force, then Newton's third law says the force on 2 by 1 is the opposite of this. So that's 18.3 repeating 0. Or the opposite direction and the same magnitude. And that better be what we got before.